Lew Tucker, thanks a lot for talking with me about this. And as I mentioned, it's essentially the legacy of thinking machines, the connection machine, and at some level, all the AI that was happening 30 years ago this year when the first connection machine came out, the ideas that went into the formation of the machine, of thinking machines, what you were working on, and how has that developed over the last 30 years?
Sure.
Why is AI, maybe you can also start there, why is AI all of a sudden a topic again?
Yeah, I think, I think it never went away. AI has been a topic almost since the beginning of cybernetics, computer science, and everything else. Minsky goes way back.
Turing test goes
That's right.
further back.
But I think now we finally have the computational power available to just about anybody. Whereas 30 years ago, we had to build it. Right. And that's what the origin of the connection machine really was, is wanting to build, as the tagline was, a machine that would be proud of us. That kind of self-reflective notion that we wanted a thinking machine. And our model at that time was the brain. That we had, a large number of very small processors, very weak processors similar to neurons. But when you put them all together, you had enough computational power to start to approach some of the problems in AI. Today we have that on the internet.
And so in retrospect, do you think that actually was a reasonable model to use?
Yeah, absolutely. I mean, for that time, it was the best we could do. We really had not very fast processors. We were several orders of magnitude and iterations of Moore's Law time ago that we just could not, accommodate the kinds of algorithms and the data sets. The other reason why I think it's happening now is what was missing back then was the amount of data, amount of digitization. Yeah, how much of the world has been digitized? Now you can run experiments on Google Images. And on Facebook, you can have this enormous amount of information that's available to researchers on the web. We've got video in it. We've got consumer video cameras, and the consumerization of computing has dramatically reduced the costs of memory, storage, and everything else. So, you have a lot of data. You have much faster machines, and that can be used together.
At what point do you think that the amount of data available got to a threshold, and at what point do you think that the computing power got to a threshold to make it possible?
I think it is on the order of 5 to 8 years ago.
So that would be 2010?
2010, 2008, 2010, I think that we started to see the aggregation of fleets of machines, very, very large data centers driven primarily by the large service providers and Google and Amazon that could aggregate. I'm in cloud computing now, and that's just another incarnation of this. How do you aggregate large numbers of machines that can be put together to work on the same problem?
At what point did you join Thinking Machines?
I was trying to think. I think it was 1986, 85 or 86. The CM1 had just come out.
That would be 86.
That would be 86. Okay, so I joined right. I think the machine, we had just launched it. I was there, I think, on the second day after it was launched.
I think the launch was April, and towards the end of April in 1986.
Yeah. And I had previously been at Cornell Medical School in neurobiology. So it was, and I had finished my PhD in computer science. And I was in AI. And so I really switched from trying to understand how the brain worked from a biological basis to simulating cognition. And a connection machine, and what Danny was doing was exactly what I wanted to be doing. So for me, that was just a thrill of my lifetime.
Did you know Danny or any of those people beforehand, or how?
No, I had read some of the work because I was an academic and trying to going to different conferences and presenting what was largely based around expert systems and prologue and reasoning and things like that. And then I started reading about the connection machine, and I believe I met Danny at at a conference down in Miami Beach, and started talking to him, and then also Tommy Poggio, whose work I had started to follow. And so that brought me to thinking machines.
And so you thought, coming from a biological, neurological background, you thought it was a valid model and that it was the right way to go forward?
I thought it was a reasonable model. I think that there is still, even at that time, there was a lot of beginnings of neural nets where we were, and sort of the line between trying to simulate what biology is doing and see if you could produce computation out of that. And completely different models around statistical pattern recognition. That was the big challenge then. Which was the right direction? Did you have to do it the way the brain does it, or can you do it in a different way? We would often say, I think, that if we wanted to attract funding and everything else, we'd call it AI. When we needed to make it work, we'd use pattern recognition. And I was in machine vision at that time, and so there was a lot of statistical pattern recognition techniques that still required enormous amounts of data, or images were getting bigger and bigger all the time. So you needed large amounts of memory in order to do these kinds of problems. So for me, the attraction of connection machine was actually that we could fit an entire image into the memory of the machine at a time. And even then a video image, we could start to do frame by frame analysis. So things such as motion and structure from motion were a lot of the early things that we were doing with the machine.
And what was the size of the images and the video images?
I think they were 256 by 256. That was a big image.
Right.
But compared to what you could do with normal computers at that time, the usual things, that was large.
Just to jump all the way into the current time, I was looking at the information on what is the largest, fastest computer in the world for the last, I think, 5 years. It's been Chinese supercomputers. And I think, I can't remember now exactly how many, I think millions of processors it has, but it's still way beneath the billions of processors that they
we're still several orders of magnitude below what we think the computational equivalent is in the human brain. But again, it's an inexact comparison. But also, I think we're looking at what are the right algorithms and how do you approach, the solution that you're trying to get with the algorithm or whatever it is processing. If we're seeing right now, autonomous vehicles and things like that, which actually we started to work on back at that time, again, but that was severely underpowered. We couldn't begin to do the processing in real time that you could do today. But in fact, many of the same algorithms are still being used. So it's surprising that I think that we've seen advances in the scale and in the amount of memory and the speed, but the advances in the algorithms are now only beginning to come out. And so that's kind of interesting at this time.
Danny also told me, Danny Hillis, the main inventor of the machine, told me in the interview I did with him that actually there is a very direct line between, for instance, the connection machine and Google through Sergey Brin, one of the co-founders of Google, who programmed the CM2 at University of Maryland as an undergraduate. And Danny says the programming paradigm that he had developed to map a problem out onto thousands of processors, then bring that back in and reduce it down to an answer that could be used for the next step, was turned by Sergey Brin into the MapReduce algorithm.
Yeah, in fact, MapReduce is, on a connection machine, there's an instruction, which was a scan, and a segmented scan, which is the essence of MapReduce. And we had built that in as a primary instruction of the connection machine itself. So it's not surprising, because when you start approaching a problem, and we called it data parallel at that time, and that the parallelism is in the data itself. The simplest model is always that of an image. If you've got 10,000 pixels in an image and you assign each pixel to an individual processor, you could, in a single unit step, perform the same operation on all 10,000 pixels. That data parallel way is the way that that was perhaps the most intriguing part about programming connection machine, because everything that we had been taught before about optimal serial algorithms and how to reduce the number of steps got thrown out the window. And the analogy was always you tried to turn the problem on its side and look at it from the data side, and then how could you process all this data at the same time. So a simple case might be for a video stream of, let's say, 10 minutes, you would take each frame and process that individually on a processor, and therefore get large chunks of the video pipeline processed in real time.
So each frame would be, each pixel in the frame.
You could have either each pixel in a picture assigned to a processor if you're doing very fine grain, or if you had each, and a lot of the movie studios were starting to use the connection machine for processing films, and they would assign an entire building of an entire frame to a processor. And therefore they would be able to do 1,000 frames at a time, let's say that 1,000 processors. And today's machines today, which are now in the cloud, can do much the same thing, because they now can get thousands of processors working together on the same problem at a much, much higher rate than ever before.
So parallel programming, certainly at that point, was considered an impossible task. And well, Friedrich once told me, well, yes, if you take undergraduates who have been taught how to program serially and then try and teach them how to program in a parallel mode, then they'll be very confused. But if you take raw, unformed minds and just start out with parallel concepts, then they'll think it's very natural and they won't have a problem. But as far as I know, at least, for instance, the Harvard CS50 introduction to programming is very serial.
Our languages today are still serial languages. I mean, in many ways, we've taken a couple steps backwards. When we started working on a connection machine, the languages, first we had designed our own chips because they didn't exist, our own networking capabilities because that didn't exist, and then we needed to create our own parallel languages so that they were, in many ways, the only analogous language available at that time was APL, because APL had array operations. So you could say add array A to add array B, and that would be a unit operation in which each element of the arrays were being added together. So we came up with C* and Fortran 90 and other languages which expressed array operations so that we could think parallel. And then once you started thinking that way, yes, it was very hard to go backwards. But we had all been trained, I think, in traditional languages. And now the languages that people are using are, again, back to pretty much serial languages. We have minor capabilities in terms of hyper-threading, because our processors today actually have multiple cores on them. And so you get multiple threads, but a small-scale parallelism, not the massive parallelism that we were trying.